So this is lecture 12 on the Bolzano-Weierstrass theorem, and here it is. Every bounded sequence of real numbers has a convergent subsequence. Interesting. So why is this true? Well, suppose we have a bounded sequence. All right, then we define A as the range. So there's two cases to consider. Either A is a finite set, or A is an infinite set, and the proof is going to proceed on those terms. So if it's finite, then that means that there has to be an x in this set, which is repeated infinitely many times, right? If that wasn't the case, then it would be infinite, because we have to give, a sub n for an infinite number of, indices. So it just stands to reason that if it's finite, there must be a repeat infinitely many times. And so we can let n1 be the smallest n in the natural numbers for which an is equal to x, right? You could look at the set of indices for which an is equal to x, use the well-ordering principle to pick that n1. And likewise, you can pick n2 to be the next one, which is equal to x, by, again, you can consider the set of all n for which an is equal to x, call that sx. n1 is the smallest of sx. And then you remove n1 from sx, that gives you a set of integers which is not empty. Again, because this is an infinite set, so you can't exhaust it after a finite number of steps. And then you can apply the well-ordering principle to this. That picks n2, right? And we can continue in this fashion since sx is infinite. And so, okay, great. Well, then the point there was then that we have this constant sequence, right? Constant subsequence with the n1, a sub n2, and so forth and so on. So that's the convergent subsequence we're looking for. On the other hand, if a is infinite, then we note that it's bounded, right? We're assuming it's bounded. So c is less than or equal to a, n is less than or equal to d. And we can define a sequence of nested intervals by targeted bisection. All right, and so we'll begin with I1 is equal to the closed interval from c to d. And since a is infinite, at least one of, the midpoint with the endpoints has to be infinite, right? At least one of them. If they were both finite, it would contradict the infinity of a. So, or the infinitude, I don't know what you want to call it here. So, come on. There we go. Close enough. So either this has to be infinite or that has to be infinite. And so whichever one of them is infinite, or if you find one that's infinite, call it I2, right? And then we select I3 in the same fashion after subdividing I2 and picking the infinite side, and so forth. So in this fashion, we can construct a nested sequence of intervals, each of which has infinitely many points in A. Moreover, the length of these is going to 0 because they're formed by bisection, right? And so that means that the intersection of n equals 1 to infinity of in is equal to x naught by the nested intervals theorem of the previous section. All right. And so I think I got distracted when I was writing notes. I think it still remains to prove that the there's a convergent subsequence, right? Excuse me. So let's see here. So I think you could use, what could you do? You could either use the left endpoint or the right endpoint of the intervals which are nested, I think, because those must converge to x naught, and those would give you, well, that's not quite it either. You have to pick you have to pick you have to pick a string of elements in the range of the sequence to get the convergent subsequence. So let's see, here's how it goes. For each one of these subintervals, we should pick a something in the sequence, right? And then call that like the first thing in the subsequence, and then we bisect, right? And make sure we don't, and then pick something in that next subinterval, right? And call that the next thing in the subsequence, and just continue picking an element in each of one of the nested intervals. So, interesting. One second, guys. I feel like I'm shortchanging the textbook here for a second. I mean, I'm happy with my notes for the rest of this section. It's just something, I feel like there's something I forgot to write down here. Maybe. Oh no. Oh, my camera's okay. I thought I'd done it in. All right, well, here's the textbook. Let's see if I've missed something. I mean, it's all right. So for the case it was finite, he defines the convergent subsequence basically by just like I said. All right, great. If A is infinite, all right, so he does his bisection, gets the nested intervals, right? Here's the part I was missing. Now construct. Now we now construct the desired subsequence AN as follows: that N1 equal to 1. Choose N2 greater than N1 such that AN2 is an element of I2. Okay, this is possible since I2 intersect A is infinite. All right. Next, choose N3 greater than N2. We need to do that so it's a subsequence, right? Such that AN3 is an element of I3. And just keep doing that. Just keep picking A sub NK as an element of IK. And you can do that for all of the bisected intervals. Okay, and then it must be that, of course, they have to converge, right? Because of the nested intervals property. Yeah. So, let's see here. Well, he's got, maybe I'm missing a squeeze theorem argument here as well. So it says that IN equal to CN dN. Of course, the limit of that is equal to 0. And we know from the proof of the monotone convergent sequence theorem that CN converges. Say that the limit of L is the limit of CN, the limit of dN is that, which is also equal to L. So we've got CK and DK. Oh, very, very good. This is the thing I'm forgetting. It's like, so basically the thing is, you've got in his notation CK and DK. These are the, IK is CK DK in his notation, or their notation, I should say. And the thing is, they're selecting ANK from there, right? And so because that limits to L and that limits to L, and this is between those, by the squeeze theorem, this subsequence has to converge to L as well. Very good, very good. That, I knew I'm missing something in what I've written, so there's what I was missing. Sorry about that. I must have, I obviously must have gotten distracted between page 1 and page 2 and talked myself into having more written than I actually did. I think my camera's gotten bumped. I can't get the, oh, I know what it is. I zoomed in. Duh. All right. So next up is the concept of a Koshi sequence. So Koshi sequence is a pretty big idea. And it turns out that Koshi is kind of just another way of looking at convergence for real sequences, but that's not always the case. If your space is not what's called complete. But in any event, here it is. A sequence an in R is a Koshi sequence if for any epsilon greater than 0 there exists an n such that whenever you pick m and n larger than big N, we can have that the distance between a sub little m and a sub little n is less than epsilon. In other words, you can, in a Koshi sequence, you can pick an integer large enough such that any two elements of the sequence in the tail past that number, they're you know, as close together as you'd like. You can pick an n to make them as close together as you'd like. And here's the big theorem. Convergent well, this is not the big theorem. This is an easy theorem. Convergent sequences are Koshi sequences. Convergent implies Koshi is the theorem here. And that's a pretty simple calculation. Here it is. So suppose AN's convergent sequence, AN goes to AN, goes to A, and then for any epsilon greater than 0, we can make AN minus A less than epsilon over 2. And so if we pick M and N, and those are larger than N, then check it out. We've got AM minus AN less than or equal to add and subtract A, triangle inequality, and then, you know, flip it because its absolute value of thing is negative, is equal to, you know, the absolute value of negative, the same thing. But by construction, that's less than epsilon over 2, and that's less than epsilon over 2, so that's less than epsilon, which goes to show you what? This is less than epsilon. M and N were arbitrary, and we picked an N. In other words, we've just shown that the sequence is Koshi. Woohoo! So convergent implies Koshi. But we get more. In fact, a Koshi sequence is bounded. Here's the proof of that. If AN is Koshi, then we can pick epsilon equal to 1, and we can select an N, a big N, such that the distance between AM and AN is less than 1 for all M beyond the big N, M and N beyond the big N. So then AN minus AN. So here's the, I'm choosing the particular choice of M equal to big N. Certainly that's less than 1, right? So, okay, so you let M be the max of all these guys, and then 1 plus AN. And then notice that if n is larger than big N, you've got, well, you just kind of do this kind of trick. AN is equal to AN plus or minus big AN, which is less than or equal to, by triangle inequality, that plus that. But remember, by construction, this is less than 1. And 1 plus AN, well, that's less than or equal to M because that's one of the things on this list, right? So you notice we've got this right here, which is what we have right here, which is why we get that. Because, you know, that is larger than or equal to anything in that list. And also, it's pretty obvious that AN is larger than M for larger than or equal to M for n equals to 1 to n minus 1, because those are explicitly in this list right here. So, in other words, M serves as a bound for AN. And remember, this suffices to show that a sequence is bounded. So Koshi sequences are bounded. All right, what else can we say? A Koshi sequence. What else can we say here? Come on. A Koshi sequence that has a convergent subsequence is convergent. Huh, interesting. So it's enough to have a convergent subsequence automatically implies convergence in the context of Koshi. That's pretty cool. Let's see how that goes. So let A have a Koshi sequence. Suppose AN has a convergent subsequence A sub nk. And then for any epsilon greater than 0, of course, we can pick an n such that m and n beyond big N make the difference of am and an less than epsilon over 2. And then, of course, the convergent subsequence goes to A, right, for as k goes to infinity, which means we can pick a k, a big K, such that little k bigger than big K implies that A sub nk minus A is less than epsilon over 2. So, okay, sorry, horrible pun. So there exists an n sub L greater than n such that A sub nl minus A is less than epsilon over 2, right? Right, because if we go far enough out, there exists a k such that this happens, right? So certainly that means that we can pick n sub L such that it's within epsilon over 2 units of A. So just he's converting it from a statement about K to a statement about NL, right? And then, well, look at what you got. You got AN minus A, then add and subtract A sub NL, and then use a triangle inequality, you got that. But the thing is, this we can make small because of the Koshi criterion, and this we can make small because of the convergence of the subsequence A sub NL. And so we've, by construction, made that less than epsilon over 2 and that less than epsilon over 2, which makes this less than epsilon, which is just what we need to prove that the sequence converges to A, right? So in fact, there's a little bit more to this lemma than just what we said. A Koshi sequence that has a convergent subsequence is convergent and converges to the same value as the subsequence. See that? It's not just that it converges to that same limiting value as the subsequence. That's what the proof shows. And then finally, here's a big one, but this kind of uses just all the things we've already just put together. And here it is. Any Koshi sequence in the reals is convergent. So Koshi implies convergent in the context of real sequences. So here's the way we put together what we just did. First of all, if it's Koshi, it's bounded. But then Bolzano Weierstrass says you've got a bounded sequence, right? Has a convergent subsequence. Okay, so you got a, all right, so what, then if you've got a Koshi sequence, it's bounded, right? But since it's bounded, it's got a convergent subsequence. So you've got a Koshi sequence, which is a convergent subsequence, then by lemma 2.44, that means that it's convergent. So in short, Koshi implies convergent. And so at the start of this section, the text claimed that the Bolzano-Weierstrass theorem was equivalent to the completeness axiom of the reals. And I think we can see this in the above because we've just shown that Koshi implies convergent. And in contrast, there exist Koshi sequences inside the rational numbers for which the limits outside the rational numbers. I should mention that one way you can form the real numbers is to take the rational numbers and to adjoin all the limits of Koshi sequences. This process is known as taking the completion of Q. And so this is one of the things that analysts do is they have perhaps an abstract space. Maybe it's missing some limit points. And so one of the things you can do is just adjoin those limit points of the Koshi sequences, and in so doing get what's called a complete space. So the real numbers are a complete space because Koshi sequences converge. And then page 4 here in my notes is the example in your textbook, which is this is a pretty neat example. Yeah, I'll go through it here. First of all, the definition. A sequence is called contractive if there exists a contraction constant k between 0 and 1, 0 inclusive, 1 not inclusive, such that an plus 2 minus an plus 1 is less than or equal to k times an plus 1 minus an. All right, that's a contractive sequence. And so here's an example. It says, what's the example say? actually it's a theorem. Every contractive sequence is convergent. All right. What? Oh, so I was thinking there was an example here, but I'm forgetting the proof is kind of like an example in a sense. All right. Every contractive sequence is convergent. So I have a remark here which says that another way you can look at Koshi is that for fixed p, the limit as n goes to infinity of an plus p minus an goes to 0. So it's a way to sort of recharacterize Koshi in terms of the limit of one index going to 0 with the other one being fixed but arbitrary. So sometimes you'll see this taken as a definition of Koshi by people who want to have a more sort of computational limit-based Koshi. I've seen that somewhere. I don't remember where I saw it, but anyway. So here's the theorem. Here's the proof, rather. So suppose you have a contractive sequence and with contraction constant k between 0 and 1. So I'm going to prove by induction a little result here, first of all. Notice that if we look at a4 minus a3, we've got k times a3 minus a2, which is k squared times the absolute value of a2 minus a1. So it looks like we're getting 2 powers less than whatever's here, right? So, So suppose inductively that we have absolute value of an plus 2 minus an plus 1 is less or equal to k to the power n times the absolute value of a2 minus a1. We've already shown it's true for n equals 1 and 2. So then an plus 1 plus 2 minus an 1 plus 1 is equal to that, right? Which is less than, by the definition of contractive, an plus 2 minus an plus 1, which by the induction hypothesis is less than k to the n times the absolute value of a2 minus a1, which then is this, and that proves the induction claim, and implies n plus 1. Hence star is true for all n by proof by mathematical induction. And then here is where it gets interesting. So look at anp minus an. All right. Come on. Then that usual trick of subtract let's see here, add and subtract an plus 1, add and subtract an plus 2, and so forth all the way until we get to add and subtract an plus p plus minus 1. So, and then do the triangle inequality, it gets you the sum of differences, absolute values, and then by the thing we just proved by mathematical induction, we have this, this sum, and then we can of course factor out the k to the powers that they are there, n minus 1 to n plus p minus 2, and that's an absolute value. Don't get that should be absolute value. And then I can factor out k to the n minus 1, I get this, and then, great. At that point, I just kept going. I said, okay, well, instead of taking this finite sum, take the series that's formed by adding all powers of k. We can do that because this is a series which exists. We recognize it. It's the geometric series with ratio between 0 and 1. And so we've not proved that. I don't think that, he used this in the textbook. I don't remember that being proved yet. Maybe I missed it. Maybe it was already done. I don't know. It's probably already done. I probably just forgot. But anyway, geometric series gets me from here to here. And great. Then the thing is, as n goes to infinity, this goes to 0, and this stuff is just fixed. So we have that an plus p minus an goes to 0. And therefore, since p is arbitrary, it proves that the sequence is Cauchy and hence convergent. So that's pretty neat. And he also has an example at the end of the section showing you that k equals to 1 makes this stuff not work. So you do need that k has to be less than 1 for these things to all work together nicely. So next up is, well, we'll get to it when we get to it. Thanks, guys.